Now we're going to look at a rod rotated about its end. So this is a uniform rod again. And if you're thinking this is similar to the rod about its center, it should be. In fact, most of the setup to this is going to be different. So through the magic of animation here, let's just bring up the work that we already did for a uniform rod. Okay, we're still going to add up DMs and all that good stuff, and we're going to still take advantage of the density. Okay, of course the difference is, first of all, if you think about it, we should end up with a moment of inertia that's greater this time around. And the reason for that being is, for rotating a rod about its end, more of the mass is farther away from the rotational axis than in the prior example. So that's going to be kind of our test or our check at the end to make sure this should be greater. Okay, and we're going to find this two different ways. First, we're going to do it from scratch, the calculus-y way, and then next we're going to do it the easier way, the parallel axis theorem way of doing it. Okay, so starting from our integral, think about it, all that changes. This is still a rod of length L. Now instead of evaluating from negative L over 2 to L over 2, we're starting at the rotational axis and going to the rod. So that means we're going to evaluate from 0 to L. So this one's actually going to be easier. All right, so our integral looks like this. From 0 to L, r squared dm, and that equals r squared times lambda dr. Okay, that's once again substituting from using our definition of density. Okay, if you want to pause at this point and go forward and see if you can take it the rest of the way here, you can. Otherwise, here we go. Okay, right away, let's pull out constant density. We got a really easy thing to integrate here. So now we're going to say that integrates to lambda r cubed over 3 from 0 to L, which equals lambda L cubed over 3. And because lambda is equal to m over L, we can say L cubed over 3. And like will always happen with these, cancel one of the length quantities, and we get 1/3 ml squared. Okay. So back to what we're doing, we said it should be greater. Well, 1/3 is greater than 1/12, so it passes that whole test. Okay, and now let's just use the parallel axis theorem to confirm what we just got here. Parallel axis theorem says I, when something's shifted by some distance d, equals its moment of inertia about its center of mass plus however much our shift is. Okay, so we're going to say the rod about its center, we found a video ago, is 1/12 ml squared plus, oops, this should actually be m times distance squared. So d is the shift there, which is kind of saying the same thing as what I had, but yeah, the mass of the entire thing times kind of that d is the offset in this point. All right, so we're going to say mass of our entire rod, and then to go from the center over to the end of the rod would be a shift of L over 2, and we need that quantity squared. So this would be ml squared over 4. And now just do your 4th grade teacher proud and add together some fractions here. So 1/12 ml squared plus 1/4 would be 3/12 ml squared. And that comes out to, added together, that's 4/12, and 4/12 is 1/3 ml squared. Okay, so we got agreement there between that and what we're doing. That's a good sign too. Moment of inertia of a rod about its end. Fiend.